Walk into any hardware store today, and you'll find a highly specific tool for every possible way to move dirt. We have long-handled diggers for snapping through dense roots, deep bucket scoops for hoisting loose gravel, and massive steel teeth for shattering rock. Modern engineering has produced an exact geometric shape for every conceivable scenario, whether that's carving a delicate garden trench or clearing 2 feet of heavy snow from a driveway. For the vast majority of human existence, moving earth was the inescapable bottleneck to our survival. To build a shelter, bury the dead, or redirect water, you had to dig. For tens of thousands of years, we relied on a single universal tool to do it. This is humanity's earliest known earth-moving technology. It's a 99,000-year-old bone digging implement unearthed in China. By the Neolithic period, around 10,000 BC, humans across the globe were hunting large animals and systematically harvesting their broad, flat shoulder blades, known as scapulae. Strapped to wooden handles, these animal bones became the universal tool for excavating everything from fire pits to defensive perimeters. The legacy of that bone is baked into our language. The Latin root word scapula eventually evolved, branching out to give us the modern English words for spatula, spade, and shovel. So how did we get from tying a deer's shoulder blade to a stick to mass-producing the specialized steel arsenal that built the industrial world? As early civilizations began to scale up, they started digging deeper into harder, highly compacted ground. Bone tools, prone to splintering and snapping under pressure, lacked the mechanical strength required for serious excavation. The first major material upgrade arrived around 1750 BC. Bronze Age miners in Britain carved purpose-built wooden shovels to extract copper ore, gaining thicker, resilient blades. Then came the Iron Age. The development of metal smelting in Southwest Asia finally allowed blacksmiths to forge rigid, durable metal plates that could slice through dense roots and rocky soil without breaking. But there was a persistent flaw in this progression. While the materials grew stronger, the geometry remained static. Blacksmiths were still forging flat, generic scoops expected to perform every possible digging task. Ancient humans had successfully conquered the chemistry of material strength, but they had not yet figured out the science of design efficiency. During the industrial era, human ambition shifted to projects that physically connected cities and spanned oceans. Meeting this massive demand required organized manufacturing. Founded in 1774, America's Ames Company stepped up to forge millions of tools for this new era. This chart visualizes the global shovel market by 1874. Ames dominated the industry, manufacturing 60% of all shovels sold worldwide. Thousands of laborers used Ames shovels to manually level mountainsides and fill valleys for the Transcontinental Railroad. They were shipped south, where men scooped out millions of tons of dense, wet soil to carve the Panama Canal. And they were used in urban centers to manually excavate the sprawling underground networks of the New York City subway. Relying on generic hand tools to move millions of tons of earth exposed a massive physical inefficiency. Forcing a worker to lift heavy clay one day and dry coal the next with the same blade shape resulted in wasted energy and slower progress. In the 1890s, an engineer named Frederick Winslow Taylor was tasked with solving this industrial problem. Taylor measured the weight workers were lifting per scoop and introduced the science of shoveling. He proved that using a single shovel shape for different materials destroyed productivity. A blade holding 21 pounds of dirt would hold a uselessly light amount of loose ash. This realization fractured the tool into distinct species. First came the square scoop shovel, flattened out and equipped with high sides to maximize the volume of lightweight materials like grain or coal. Next came the trenching shovel. Engineers elongated and narrowed the metal blade, providing a precise instrument for carving clean lines to lay pipes and cables. For deep, narrow holes, the mechanics changed completely. The post-hole diggers split the tool in two, adding a metal hinge so agricultural workers could pull perfect vertical columns of soil straight from the ground. The military adapted the tool for survival. In 1908, the British Army designed the folding entrenching tool, a collapsible design for mobile warfare. By matching the tool's geometry to the physical properties of the material, Taylor's logic shifted the shovel from a blunt instrument into a collection of specialized designs. Today, earth moving looks different. Excavation sites that once required hundreds of hand shovelers are now cleared in hours by a single machine operator. But the hand shovel didn't go extinct. It retreated into the specific niches where massive hydraulic machines cannot operate: garden borders, tight irrigation channels, and localized tasks. We mechanized our horsepower, but the engineered shapes of the hand shovel, the flat scoop, the pointed spade, and the narrow trencher remain the functional standard. In 1775, George Washington's troops secured their position in the American Revolution by using shovels to dig the fortifications overlooking Boston Harbor. During the Second World War, factories supplied 11 million specialized shovels to Allied forces, granting troops the ability to carve protective trenches across the battlefields of Europe. The shovel's exact physical shape dictated how fast civilizations could lay infrastructure, extract resources, and defend territory. When you reach for a specialized shovel in your garage today, you're picking up 99,000 years of iterative human engineering.